Revision video on electric fields. Here we go. So where do electric fields come from? They come from charges. All charges create an electric field in the space that surrounds them. And we also get forces due to an electric field. All charges will experience a force if they're inside an electric field. You need to be familiar with the diagrams for different types of electric fields. We'll start off with the ones due to just point charges like these ones. The positive and negative point charges, the electric field will look like this. So it points radially outwards or inwards with nice straight lines. So you use a ruler to do this. Don't be lazy like me. With the arrows pointing outwards for positive charges and inwards for negative charges. So these field lines are important because they indicate direction and magnitude. The direction the arrows point tell you the direction that a positive charge is going to be forced. The number of field lines per unit area tell us the strength of the field, and that's true for any field. The strength is always given by the number of lines per unit area. If you need to draw the field diagram for a positive and negative charge in the same space, this is what you should do. You should draw a straight line that goes from the positive to the negative charge. Then lines coming out from the corner like that, and from the top all the way around joining to the top, and on this side it comes out like that, this side comes out like that, and then we want to mirror this on the other side. Our arrows like this, which must go away from the positive charge and towards the negative charge like that. So that if I had a positive charge and I placed it somewhere around here, like at this point here, just switch off that, it's going to be forced in the direction of the arrow, so it should be forced in this direction here along the field line, repelled by the positive charge and attracted towards the negative charge. Is the way the positive charge will move. If we had two negative charges, we would draw our diagram like this, with our field lines pointing up and away, like that, away, 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 mirrored all the way around like this. Do the best you can to make it symmetrical, but there we go. The arrows point towards negative charges, like so, and there you have it. If we have positive charges, the arrows will be pointing outwards in the opposite direction, because positive charges should be repelled, so there we go, and they're attracted towards the negative ones. Important things you should remember at doing your field lines is that they should not cross and they shouldn't leave surfaces at right angles. So if I had a charge here and I was trying to do its field line, I would, and I was trying to do one out here, I wouldn't do something like this, because that's clearly not coming out of the surface at a right angle. So what you should get in the habit of doing is, if you're doing a field line, make it go perpendicular away from the surface first, and then concentrate on whether it should curve this way or that way, or if it should just go straight out and things like that. So just be conscious of that and try the best you can to do those two things. Okay. Look at is for parallel plates. For example, we will make the bottom plate charge positively and the top plate charge negatively. You definitely want to use a ruler for this. And as we use a ruler, we want to draw our lines parallel, nice and straight, and the same distance apart. So you might want to just measure the distance between them, or you better get really good at eyeballing it. So I'm just gonna, that's about the same distance apart, so we'll do it like that, and I'll keep going to the end. There we go, same distance apart, all going in the same direction, parallel, and that shows our uniform electric field going from positive to negative. So positive charges will be forced in that direction and gain energy in that direction, and negative charges will be forced in the opposite direction, anti-parallel to the field lines. This helps us see is that the electric field is the same magnitude and direction between those two plates. Same strength everywhere. Lastly, we'll look at our pear-shaped conductor. Here, when you draw your field lines, you want to make them go straight out, nice and perpendicular to the surface, and as you get close to the sharp point, we need to draw more of them to show that the electric field is stronger near the sharp point. Then we get to flatter surfaces, they need to be further apart to show that the field isn't as strong. So they clearly should be closer together near the sharp point. So like I might even draw, I don't know, I think it's fine how the way it was, but I'll make sure you have enough there to show that they're closer together and that the electric field is stronger. So you do the arrows, so if this one was negative, for example, I'd do the arrows inwards. If it was positive, I'd do them outwards. Simple as that. All charges should experience a force in an electric field. Here's an electric field in red in this space, and I've got a charge in the field as well, so it should feel a force. How much force should it get? The amount of force it should get depends on how strong the field is, and also depends on how big the charge is, in terms of its, like, how much charge is there that's in the field to get the force. Electric field strength is given by this guy here. The electric field strength is equal to, the amount of force on the charge divided by how much charge is there. So that's measured in newtons per coulomb. So we could have a electric field that's of strength 10 newtons per coulomb. For every coulomb of charge that's in a particular electric field, it should experience 10 newtons for every single coulomb of charge that's there. So we can use this relationship to calculate how strong the electric field is, or a common way of seeing this being rearranged is that we might rearrange it to this form here. If I want to calculate the force, I'll be multiplying the electric field strength by the charge. So in any context, if we just grab the one charge and we know how strong the field is, we can calculate how much force is on the charge using that equation. As for the direction of the force, it depends on the charge. If the charge is positive, a tiny positive sign there, it should be forced in the same direction as the field. So this positive charge will be forced in that direction. However, if the charge was negative, put a little negative sign on there, then it should be forced in the opposite direction to the electric field, or anti-parallel to the field lines. Negative charges are forced in the opposite direction in the electric field. The concept that this links to is something called a corona discharge. Corona discharge results in the movement of charge away from a conductor, and that's applied in different contexts, such as inside photocopiers or inside lightning rods. We need some kind of sharp thing, a sharp point, where you've got overall charge movement that's going away from that conductor. So, if we have a conductor that is sharp, here's one that's sharp, a sharp point, and around it we'll have a strong electric field. To be sharp, that means it just generally has a small radius of curvature. So it could be like a really thin rod that has a tiny radius of cross section, and it'll have a strong electric field surrounding it. So strong that if there's molecules in the air, which there will be, it will polarize them. You chemistry people will know that that means that if I've got a particle here, which could be, I don't know, carbon dioxide or, I don't know, water vapor or something, there's some kind of molecule there, and that means it's going to have a slightly positive end and a slightly negative end. There we go, like that. And it will be attracted towards the sharp point. They reach the sharp point, an electron transfer occurs between the molecule and the sharp point. Which way the electron transfers depends on what charge the sharp point was originally, but there's always an electron transfer, and this is going to ionize the particle and give it a overall charge. So this ends up ionizing the air particle, and it ends up getting repelled away from the sharp point, and that's the charge movement away from the conductor that happens, and that's the corona discharge that we see. Moving on now to Coulomb's law. Coulomb's law gives us a way to calculate how much force is between two charges. So the amount of force that we get is 1/4 pi epsilon naught, or the whole thing is Coulomb's law's constant. The product of the two charges divided by the radius squared. So Coulomb's law constant, that whole thing is 9 by 10 to the power of 9. And we can just use that as a constant whenever we need to use it to do a calculation. The simple use of Coulomb's law can be quite specific. If we have this charge, Q1, and this charge, Q2, and we know the distance r between them, we put them into this formula and it tells us how much force of attraction or repulsion is happening between them. The equation by itself only really tells you the magnitude of the force. It doesn't tell you which way or anything. To figure out which way, we need to use our brains and think about the situation. It depends on the magnitudes of the charges. For example, if they are both positive charges, that means that they are repelled by each other. So charge number 1 will be forced left, and charge number 2 will be forced right. So we can say that the force on charge number 1 is left, and the force on charge number 2 is right. So the force that we're talking about depends on the object that we're talking about. If I'm focusing on number 1, I would say the force is however much we calculated, and it is to the left. If we were focusing on number 2, the force would still be the same, but the force would be directed to the right, because they both feel a force. You can even draw the forces on there, and there they are. The force on number 1 and the force on number 2, they're both laid out there in different directions. Usually a test or exam question will get you to focus on one charge, and so you'll only be talking about one of these forces, and so you would just have to figure out, is there an attractive force between the two, or is it repulsive, and use that to determine the direction of the force on the charge you are focusing on. We switch things up, and now this one's positive and this one's negative. The direction of the forces will change, because now we know that positive charges and negative charges are attracted to each other. So this time the force on number 1 is to the right, and the force on number 2 is to the left, because they need to be attracted to each other. That's the direction of the forces. What if there's multiple charges? If there's multiple charges, usually the examiner wants you to find the force on one of them. And there'll be usually a situation either involving a distribution like this, or they might be used in some kind of triangular arrangement where the forces are, you'd end up using equilateral triangles or something like that. And we're focusing on just one of those charges. So in this question here, we'll focus on just this charge, and we want to find what the total force on that charge is. We have to recognize that it will experience two forces because of the two other charges. So it gets Coulomb's law twice. Let's make charge number 2 a positive charge number 3 a negative charge, and charge number 1 a positive charge. That means that we must recognize that it is repelled by charge number 1. And there's the force, a force of repulsion coming from charge number 1. Now, it's the opposite charge to number 3, so it's attracted to number 3. That means that there is also a force doing this, and that is the force that's coming from number 3. There we go, force from number 3. And then to figure out the total force on charge number 2 now, we have to do a vector diagram. So figure out the direction of your forces first to make sure you get them right, and then create your diagram by adding one on top of the other. Which way around you do them doesn't matter too much, as long as you're adding the arrows tip to tail. Here's my two vectors in a vector diagram here that I'm starting to create. And then my total amount of force will be this here. That vector there is my total amount of force on charge number 2.